Hi there, this video is called Congruent Arcs from section 14.6, although it has a lot of other stuff about how to measure arcs. So just for a little context, what we already know is when we have a central angle of a circle, it's very easy to measure the intercepted arc because it has the same measure. And when we have an inscribed angle, it's very easy to measure its intercepted arc because the rule is the measure of the arc is twice the measure of the angle, or you could say the measure of the angle is half the measure of the arc. So we're going to learn a few more rules about how angles and arcs are related in other situations. So first we're going to begin with a definition here. Got a little typo. In the same circle or in congruent circles, two arcs are called congruent if they have the same measure. So they have the same measure and they come from congruent circles. So they're arcs that are just as big from circles that are just as big. And let's be careful, just having the same measure isn't enough. I could have two circles that are not congruent. I could have a 90-degree arc here and a 90-degree arc here. They're both 90 degrees, but they're not congruent. This one over here is clearly bigger. It's still 1/4 of the circle, but it's 1/4 of a bigger circle. So we really wouldn't want to say those are the same. So we've got a few theorems related to congruent arcs and things like that. So in the same circle or in congruent circles, if two chords are congruent, then so are corresponding minor arcs. So let's draw a little picture here. So let's draw two congruent circles. By definition, means they have the same radius. So here we go. I'll draw a radius like so, and a radius like so, and those are congruent. And this is saying if two chords are congruent. So maybe I have a chord like so, chord AB, and a chord like so, chord CD, and we're saying that those are congruent. So I'm not going to do this formally, but I want you to get the right idea. This is our setup. The circles are the same size, the chords are the same size. Well, let's think about the corresponding minor arcs. Are they the same size? It certainly feels like they should be from our sense of symmetry. And we can prove this using congruent triangles. I'll draw in some convenient radii. All radii in a circle are congruent, so I have a bunch of congruent things like so. Let's call this center X and this center Y. And we might notice that by side-side-side congruence, we have that triangle ABX is congruent to triangle CDY. So then we can use CPCTC to say that these angles are congruent. Well, if those central angles are congruent, then the measures of the arcs are the same, and the circles are congruent, so those arcs are congruent. So that's the gist of this. I'm not writing down everything. The trick for so many of these is draw in congruent radii and look for the congruent triangles. Theorem 14.8 is the converse. So let's suppose we have congruent circles, and this time let's assume that arcs are congruent. Oops. So maybe I have an arc like so and an arc like so that are congruent. Well, what does that mean? It means they come from congruent circles, we already know that, and they have the same measure, which means that this central angle here is congruent to this central angle here. We know that the circles are congruent, so all four of these radii are congruent. And now I can create triangles. So if I draw in this segment like so, draw in this segment like so, by SAS, I have congruent triangles. By CPCTC, those chords are congruent. So that's a very quick sketch of the proof, but you see, oh yeah, there are triangles hiding in this. What I can use, I can use what I already know about congruent triangles. Okay, so now let's talk about some other things, and you explored these already. I've said in the notes I'm not going to give a proof, but here I am going to give quick proofs. So we have what's called the tangent secant theorem. So we have an angle like so, with its vertex on the circle, and it's formed by a secant ray and a tangent ray. So this, strictly speaking, is not an inscribed angle. It is an angle with its vertex on the circle, but one of the sides is a tangent rather than a chord or secant. But we can find a similar rule about how big that is. So here's the idea. Let's suppose we have this intercepted arc, and let's suppose that I know that this is, let's say, k degrees. I'm going to draw in a diameter like so. We know this entire semicircle is 180. So this would be 180 minus k degrees. This angle right here is an inscribed angle, so that's half as much. So the measure of this angle is 1/2 of 180 minus k, which is 90 minus 1/2 k degrees. We also know that when we have a radius or diameter and a tangent, there's a right angle here. So this is 90 degrees, which means the measure of angle AXB would be 90 minus this red thing. And that works out to 1/2 of k. So it's actually the same rule we saw before. If you have this arc and you have this angle with its vertex on the circle, the measure of that angle is half the measure of its intercepted arc. This is not literally the same setup, but the rule is still take half as much. Let's look at a couple of other rules. And they're actually proved as exercises, but let's work through the key idea. Let's suppose we have two secants that intersect somewhere in the interior of the circle, but let's assume this is not the center. So, I don't think this looks perfectly centered. As far as we know, X is not the center. So be careful. Sometimes people look at this diagram and just assume they're dealing with central angles. We're not. So we're going to figure out, how do we measure this angle made by intersecting chords? So here's the trick. I'm going to draw in a chord like so. This angle like so has this as its intercepted arc. So we know the measure of that angle is 1/2 of x. Similarly, if we look at this arc, it's the intercepted arc for this angle. So this measure would be 1/2 y. Well then, what's this one? Measure of angle CXA. Well, we can use the 180 rule. There are 180 degrees total in the triangle. We've used up 1/2 x. We've used up 1/2 y. But then the original one we were trying to find here is in a linear pair with the one with the purple dot. So the measure of angle AXB is 180 minus this thing we just computed, which works out to 1/2 x plus 1/2 y, or a better way to think about that is x plus y. So here's the idea. I'm trying to figure out, how big is this angle? I look at the arc in front of it, and that has a measure of x. I've got this vertical angle back here that has the same measure, so I'm going to look behind. That has a measure of y. If this were a central angle, these would be the same. These angles are the same, but the arcs are not the same because we're off center. So what you do in a case like this is you look at the arc on one side, you look at the arc on the other side, and you average them. Add together and divide by 2. So basically the way to remember this is that it's an average. Let's look at another case. Let's suppose here we have two secants that intersect outside the circle, and I want to figure out how big is that angle. We're going to do another trick with triangles. Let's draw in this segment like so. This is now an intercepted arc for an inscribed angle. So this angle right here has a measure equal to 1/2 x. This is the intercepted arc for this angle. So it has a measure of 1/2 y, which means that this one here has a measure of 180 minus 1/2 y. So now focusing on this triangle, triangle CMB, I'll use the 180 rule. The measure of angle M would be 180 minus the measure at this angle, which is 1/2 x, minus the measure at this angle, which was 180 minus 1/2 y. And if you work through that, you get 1/2 y minus 1/2 x, or y minus x over 2. So it's kind of the reverse of what we did for this one. Here, when the intersection happens inside the circle, it's add the two measures of the arcs and divide by 2. Here it's subtract. And you just subtract them with bigger minus smaller. So we have a few different rules now. We have a rule for measuring an angle when the secants intersect outside the circle. We have a rule for measuring an angle made by intersecting chords. We have a rule for an angle formed by a tangent and a secant. And then we have those old rules about central angles and inscribed angles. So let's just practice for a little bit. So in a case like this, how would we find the measure of angle ABC? Well, it's formed by a tangent and a secant. The intercepted arc is 250. So what's the rule? Right? For all of these, pause before I reveal the answer. Well, it's 1/2 the measure of its intercepted arc, and that's 125, which looks plausible from my picture. Here's another one. Here's angle 1. It's formed by intersecting chords. If I have an 80-degree arc here and a 180-degree arc here, how do I find the measure of angle 1? So hopefully you remember this is the case where we just average how big is the arc in front with how big is the arc behind them, and we get 130. Let's look at this one. This one's a little bit different. I'm telling you how big this angle is. I'm telling you how big this arc is, and we don't know how big this arc is. Let's call it x degrees. So here we have secants intersecting outside. The rule for that one involves subtraction. So the measure of that angle is big arc minus small arc over 2. To solve this, we can multiply each side by 2. So 50 equals x minus 30. And if we add 30 to each side, we get 80 degrees, which seems believable from my picture. All right, there we go. That is the end of this section.